Welcome, everyone. I'm Puzhao Zhang from KTH, and currently I'm a research scientist at Division of Geomatics. And today I can talk about our recent research on multi-source satellite remote sensing for wildfire monitoring, especially using deep learning. As you may know, that remote sensing data, they are thousands of satellites are acquiring data with different sensors like optical, radar, and LiDAR. This multi-source data, it can be used in various applications. And especially since the launch of the Landsat, the first Landsat satellites, we have more than 50 years satellite data so far. So it has quite potential ability to be used in various like the urban monitoring, river dynamic monitoring, and also to estimate biomass and also ecosystem modeling. But with this huge amount of satellite data, we also facing some challenges, like we lack of label data and also the poor generation performance across regions. And there's also the modality gaps between multi-source data and how to learn efficiently from large volume remote sensing data, and also how to model very long time series and to detect the changes among this huge amount of data and also the time series and the inter-year changes. So a lot of changes exist. So here we mainly talk about the topic on wildfire. So wildfires, it's increasing globally and also it's expanding to the Arctic regions, like Eurasia, and also in 2018, Sweden also experienced several large wildfires in mid-Sweden. And also wildfires can lead to air pollution and also forest loss, biomass emission, and CO2 emission, and also will lead to the property damage, like cars and also houses, apartments. So we need to do something to prevent these kind of damages to our human societies. Why do we want to use Earth observation data or remote sensing data for wildfires? Because wildfires, it happens globally. And if we want to do it more efficiently to monitor wildfires at a global level, satellite definitely is the best choice so far. And it can monitor vast areas, and especially some areas that it's not accessible to people. And also it's cost effective. We can launch several satellites, radar, optical, and it can acquire data at maybe certain temporal frequency, and also some temporal or spatial resolution. It can periodically take photos and to monitor the changes. And the most important thing is that it's temporally comparable. So we can use this the data taken at different time and compare them to detect the changes. So what kind of data can be used for wildfire monitoring? We're using optical and radar data for this research. Why it can be used for wildfire detection? From this figure, we can see that there is significant difference in the signature between burn area and health vegetation. And we can see when vegetation was burned, we can see the significant drop in the near infrared band and increase in the short infrared because of moisture loss and also the chlorophyll reduce. So based on this phenomenon, we can design some indices to highlight the changes of the forest loss. So some very widely used indices, it includes NDVI and normalized burn ratio. And also we can also use another version of normalized burn ratio based on two short infrared bands. So that's the reason we can use optical for wildfire detection. On the other side, we could also use radar data for wildfire detection, because sometimes, especially for ongoing wildfires, cloud and smoke can exist and happen. So it can block the optical observation. So we could use radar data because radar data is using longer wavelengths. It has the capability to penetrate the cloud and smoke and to sense the information under cloud and smoke. So here we use this figure to illustrate the mechanism that can be used for that using of that star data for wildfire detection. Like in the pre-fire condition, volume scattering is dominant for healthy tree. If it's burned, we can see here, but the main branches and stems kept. So we can see the dominant starback scattering. It becomes a double bounce and also surface scattering. But if it's totally destroyed, then the surface scattering is the dominant scattering mechanism. But on the other hand, that SAR is also hard to interpret, and it depends on a lot of factors, both like scene properties and also sensor properties, like wavelengths, polarization, local incidence angle, also is important to also the imaging in geometry. On the scene side, it's the roughness and also the surface geography, moisture, permeability. All these factors can affect the final signal received by the radar sensors. It's compared to optical, it's more complex. So here we compare the time series between Sentinel-1 and optical, Sentinel-2 and Landsat. Here we plot the Landsat and Sentinel-2 together in a single time series. So compared to Sentinel-1 optical, we can see a very significant drop in these three indices. So, but for the radar, we can see some variation along the time series, even for the pre-fire time series. So here we propose a SAR-based key map to highlight the changes between post-fire and the pre-fire imagings. This we call it the key map because we defined the pre-fire time series, the average, temporal average and standard deviation, and to characterize the pre-fire condition of the specific site or location. So by defining this ratio between the backstream changes and also the temporal standard deviation between 2 months pre-fire period, we have this formula to represent the changing, a kind of a relative changing measure as measure. So here we call it key map. So why do we want to use maybe like medium resolution data to monitor wildfires? Because we already have some products available, like the MODIS and VIAS. They have delay data and delay active fire products, but at a closer resolution. Like MODIS at 500 meter resolution, but it also have 250 meter bands, like near infrared and red bands. At VIAS, it's taken photos at 375 meter resolution. And we can see that usually MODIS and VIAS this is the products based on the active products. We just accumulated the active fire points to produce a progression map here. But we can see compared to Sentinel-1 here, both MODIS and VIAS, they overestimate the burn areas inside the polygon because we have used the fire parameter to mask out unburned areas outside this polygon. So we can see that here MODIS overestimated the burn areas because inside this polygon, the white polygon, there's unburned areas actually, and we can see from Sentinel-1. So we would like to use a higher spatial searching data to have more precise estimate or detection of the burn areas. On the other hand, like here, we can see the thick smoke here. It blocks the optical observation because the optical cannot reach the ground and also cannot see through the clouds or smoke. So to facilitate the monitoring, especially from denser temporal dimension, so we propose to use SAR data, as you can see here. SAR data can be used to highlight the burn areas you see here, and we can clearly see the progression based on SAR data itself. And also here we have maybe like we just based on the thresholding approach, we can see even based on the simple thresholding method, we can achieve a quite good result here, because here we just overlay the star-based results on the top of the Cento-2 force color composite, and we can see a clear high agreement between these two. It means that SAR has good capabilities here, especially at least for this wildfire events for the progression mapping. So that's the reason we would like to combine both to have a denser observation on the wildfire progression. Here we show an animation. This is the original star data here, but it's in the force color composite. It's a cross ratio, VH and VV. They are corresponding to the red, green, and blue bands. And this is optical in true color. And from the post-fire itself, in spatial for SAR, it's hard to see the burn areas. But if we use key map, and we can visually see the progression here from SAR data itself. And here we also visualize in different force color composites. It's a two short infrared band with and also near infrared band, and we can see the burn areas. This is the Sydney wildfire happened in 2019. At the beginning, when we started this project, we proposed this architecture. First, we have the pre-fire time series and also ongoing time series. We first calculate the difference between pre and post images to have the log ratio imaging. And also based on the pre-fire time series, as we mentioned, we propose the key map here based on it's kind of the relative changing indicator. So with this key map here, and we propose to use, we set key 0 as the threshold. We use the value 1 here to binarize the key map to produce a pseudo label here. And then we have the input data. We have pre-data, pre-imaging, and pre-fire imaging and post-fire imaging, and also this is the average image, and this is the standard deviation. We stack them together as input data, and here we have cosmic labels. We prepared a data set here for this single event, and then we train the convolution neural network model, and then predict the results and apply on the whole progression day by day. So here we publish this work in Scientific Report in 2020. And later, because neural network is still the convolution neural network here, it's a pixel-wise inference architecture. So later we use the UNet to replace it. And also here, we combine the Cento-1 SAR data and the optical data together to monitor wildfires. Like we have Cento-1 SAR time series and also Cento-2 MSI time series. We calculate the DMBR for optical observation and then binarize with a threshold 0.1. And it's commonly used threshold to binarize DMBR. And here we also use the same key map to produce a pseudo label. And then because optical has quite good capability to produce a good burn area results. So we accumulated, like for example, for this star date, we will accumulate all the burn area detected before this date. So we have a better pseudo label for the star data here. And then we train the model in a progression-wise manner. And the loss function, we combine to use the death loss, focal loss, and also here we have the keep response loss because we we use the two head unit here, one head for SAR prediction, one head for the optical prediction. Like here explains, we have two heads, one for optical, one for SAR. When we use optical data, we will keep the response of SAR branch. When we're training with the SAR data, we will keep the response of the optical branch. So we let the optical data and radar data, they share the same encoder and decoder, but different heights. So this is the total loss function. And we produce this result here. This is the visual result, and we have center 1, center 2, center 1, center 2. And we have the improved SAR reference. And here we can see this is optical, and then we will accumulate all the burn areas before the state together to here. So we compared the continuous joint training and the learning without forgetting. And we can see learning without forgetting, even with the ongoing date or incoming date itself, it also can reach a similar accuracy to the continuous joint training. And also on another side, the Sydney wildfire, and we can see the high agreement between optical burn area and also SAR-based results. And but for this single event-based model training, because it was only trained on a single site, it has limited performance on other area unseen data. So here we prepared a slightly larger data set composed of 16 globally distributed wildfire events, but most of them are from the North America, especially Canada and the US, and also 2 from Russia, and also 3 from the Australia. We used the red polygon areas as training and validation sites, and also for progression, we use the blue polygon areas. So here, first we derived the key map based on the formula we proposed in the profiles style. And we can see for different sites, the burn areas have different color. What does it mean? It means that the contribution, like we visualize this data, the key map in this, the red band is K cross ratio, and also the green band is KVH, and the blue band is KVV. So different color means that these 3 bands have different contribution to this visualization. So it also based on this data, that it's quite challenging to detect or binarize directly, because different bands, they have different contribution and also different thresholds for detecting the burn areas. So that's the reason we would like to use a deep learning model that we don't need explicitly to choose a threshold, and it can automatically learn or complex representation to find the burn area or detect the burn areas. So here we proposed total variation regulates unit, because for radar data it has quite strong spectral noise. So we would like to surprise the spectral noise in SAR data, especially. And we have the key map as input. And we also produce the SAR reference and optical reference. Optical reference, we also use the fire perimeter data to mask the false alarms outside one area. Then we train this model based on the 16 wildfire events, and then we apply it to unseen wildfire events and to see the performance on unseen data. And finally, we can produce a progression map like here. So here is some quantitative comparison on this TV regularized unit. And first, we compared the results based on the optical reference. And also we set different values for gamma, the weight of the TV regularization. And here for optical, we can see that with or without TV realization, it seems to achieve quite close results, especially between 0 and 0.1. And when you increase the TV realization, it will decrease the accuracy for optical reference based. Because optical itself, it has quite good results even without the TV realization. So this is mainly designed for the star data. And we can see here, when we use a larger width for the TV realization, we can see a significant increase in the F1 score and LU score. Here we achieve the high accuracy, and also the TV realization, and the loss is decreasing along this when we increasing the width of the TV loss. So here, this is the visual results, and the first column is star reference, and this is every result was compared to optical ground truth, and we can see some here. It's without TV realization for star reference space, and with TV realization, we can see the noise can be significantly reduced compared. And also we can observe the similar phenomena for this the middle two columns. And the last one is optical reference based, and we can see optical definitely it produces better results even compared to star based. And when we apply the trained model on the full progression, and we can see the first row, it shows the results, it's star-based results with star reference without the TV realization. And here with TV realization, you can see the red dot noise was removed significantly, and we can see the burn area can be quite well highlighted here and detected. And this the last row is the optical reference base, and we can see these two achieved quite similar results. And to have a closer observation, we can see here it looks a bit noisy here, and we can see this is because we have polygonized the results, and we can see here less dots, less red polygons. It means that the noise was kind of reduced. And but optical definitely it can better it can detect more or large more burn areas than the optical one. Optical may has than the star reference based because it made some maybe like the low burn severity areas because of star is not sensitive to that maybe like small changes caused by slightly burning. And also another area, and from this we can see this is also similar phenomena, but optical very significantly overestimates the burn areas in these results. So to have a better understanding on the different sensors performance on burn area detection, especially for forest area and like here, we know that multi-frequency star has different capability to sense trees. Like for this Australian pine tree, we can see that X band is sensitive to leaves and small branches, but C band is maybe like it's more sensitive to maybe slightly larger branches, but L band is mainly sensitive to branches, including the stems, and P band here, and also the with a long wavelength, it has a less sensitivity to small objects. So we proposed to prepare a large-scale multi-source remote sensing data for fire comparison between different data sources. Like here, we have 3 different sources. Center 2 optical, and center 1 C-band star, and all ILOS pulsar, L-band pulsar. So based on the historical fire information from the official agencies, we will query based on the 5-year and also the fire start date, end date, and also the specific the region of interest. And we query the corresponding sensors data. And so we prepared the biotemporal data here. including pre-fire imaging and post-fire imaging. Like here, this is optical, this is post-imaging. We can see clearly in optical post-fire imaging, and it's in red. And pre-post, this is C-band. You also can clearly see this wildfire burn area. And pre-post L-band, but visually, it looks not that clearly compared to Sentinel-1. And also, we rasterize the Landsat-based reference and into raster. Because originally it's polygon data. So we have these 3 different sensors and the corresponding Landsat-based reference. So we were involving 4 different sensors for this data set. And on the other hand, we, for wildfire, especially, we also have different resolution of reference data. Like we have the fire CCI, in 250-meter resolution, and MODIS daily burn area products in 500-meter resolution. So we have both Landsat reference and also lower resolution reference. How we could, because lower resolution reference is globally available, so maybe we could use this kind of information to train more powerful model for our global applications, because we definitely would like the model to have a better global generation ability. So here we start with Canada area. Especially because we first consider the availability of the Sentinel-2, Sentinel-1, and also ALOS data. And we first start with these 3 years from 2017 to 2019. And we visualize here the spatial and temporal distribution, and also the distribution of different land covers. And we can see the close forest accounts for maybe more than half of the total land covers. And also you see we also have involved different kinds of land covers in this data sets. And in total, we have 328 wildfires. Because we have skipped some small wildfires, we only kept wildfire with a burn area larger than 2,000 hectares. And additionally, we take the wildfires in 2019 as the testing site, because we would like to simulate the scenario that we would like to train based on the historical data, and to do testing or to prediction on the future wildfire events. So here we have the direct comparison on the temporal changes in burn and unburned areas among different land cover types. And here this figure shows the DMBR between burn and unburned area. And we can see DMBR for unburned areas is close to 0. The median of the box plot is close to 0 for different land covers. But for the burn areas, we can see it has a larger range, and also the median is increased to more than 0.3 for shrubs, and also for the forests, seed forests. And different land covers may have different range in different distribution. But for C-band radar-based log ratio imaging, we can see that burn area or burn pixel and unburned pixel, they have a larger overlapping between them, and it's really hard to find a threshold to separate burned and from unburned areas. But for optical, it's easier to take a threshold. Like here, we can take a threshold, maybe like 0.1 to separate burned and unburned areas. Definitely, maybe there's also some false alarm or missed classified pixels, but it's clearly that we have the clue that the threshold locates. And when we compare more bands, like we only compare the C-band post imaging, and we can see the distribution still with a larger a large overlapping between point and point. And after we do the temporal difference, it's based on log ratio. And we could also see the overlapping between point and point. But it seems that VH have a better separability between point and point pixels than the VV for center 1 C-band. And this is ALOS L-band star background changing. And we can see here, this is the post-based. And here for forest area, we can see L-band is it's better than star, than C-band star in separating point area and unbound area. And here it's log ratio based, and we can see it has less overlapping than C-band star. It means L-band probably have better ability to distinguish point and point areas. So based on UNET, we also did the channel evaluation to see how different bands perform in point area detection. And like here, we defined different composition. Like here for center 2, we defined the post 8. We only use the 3 bands, right, near infrared, and short infrared, but we only use the post imaging. And pre-post 8 will use both pre and post imaging. And for center 1 and ALOS, we also compare different bands, VH, VV, and normalize the difference between VH and VV to have a comparison between different bands. And also the post means that we will use all 3 bands, but only with post imaging, post-fire imaging, and pre-post we use both. So from this figure, we can see that still optical pre-post will achieve the highest accuracy in center 2 across training, validation, and test. When we remove the pre-fire imaging, the accuracy slightly decreased, especially for the testing sites. And also for ALOS and the center 1, and we also see that the pre-post setting achieves the highest accuracy, and you can see the green box plots. But for radar data, if we remove the pre-fire image, we can see the accuracy decreased very significantly, especially for center 1. So it means that for radar data, we better to use both pre and post imaging to detect the point areas. But for ALOS, and we can see here, this is normalized difference between VH and VV that achieved better accuracy than the other 2, VH and VV itself. And also for center 1, and we can see VH achieved a slightly better result in the testing sites. And to have the comparison, better understanding on the fusion of the different sensors, we also investigate different architectures here. We have the UNET early fusion. We stacked pre and post imaging, and also different sensors together to do the prediction with a single UNET model. And we also have 2 different SAMIS architecture. So we could share the encoders, or we just let different, because for different sensors, it's not meaningful to share the encoder. And so we let each sensor have their own encoder, but we can, here we can concat the features or do the difference between these 2 temporal inputs. And also this is a late fusion model. We have individual units, and then we've only fusion the result together at the final layer. And we use the feature space, use the feature layer and stack them together to have the final prediction. And here is the results that we compare the fusion results with the individual sensors. And compared to Center 2 itself, we can see when we combine Center 2 and an ALOS or Center 1, we can see a slightly increase in accuracy. And also here, when we combine these two sensors together, C-band, L-band, we can achieve the high accuracy too in area score. But the previous learning is all fully supervised learning. But you know, for some areas that with no labels, it still may have the limited generalization and performance. So how shall we handle that? Like for example here, for Canada area, we have very good labels. It's Landsat based. But for Alaska and US continental, so we assume that we don't have very good labels because we have some labels like the fire perimeter, but it's not that accurate. So here we would like to use the domain adaptation approach to improve the generation and performance across regions. Like here, we define the Canada area with labels as the source domain, and the areas without good labels as the target domain. The aim is to improve the performance of the model in the target domain, where there's no good labels. So we enlarged the previous dataset into the whole North America, like include these three areas because we separate Alaska from the US because Alaska and the US have quite different climate zones. Because also Alaska has similar climate zone to Canada. So here this is the overview of this dataset, and we have three regions, and Canada, Alaska, and the US continental. We have different reference because for Canada, we have quite good references from it's called NBAC, and we have this number of wildfire events. For Alaska, we have 129 wildfire events from 3 years, and also US, we have 285 wildfire events. And the total number of patches is listed here. So this is source domain and target domain. In the source domain, we have the input data and also high resolution labels. But for target domain, either we have no labels or we have low resolution labels. Low resolution labels can be from the fire CCI or MODIS progression data or MODIS one area data. So we would like to investigate how these contribute to improve the performance of generation across regions. So first, we propose this unsupervised domain adaptation approach. We assume that there's no any labels available in the target domain. So here, we stack the center two pre and post imaging together as the input for one branch. It's an optical branch. And this is for star branch. We have center one star data, also with bitemporal stacked data. So we also have a fusion branch. Here, we would like to stack the features together from optical and the radar branch, and then we make a prediction for the fusion branch. And we have for the source domain, we have the high resolution labels, so we can calculate the supervised loss. But for unlabeled data in the target domain, we propose this consistent loss. The consistent loss is used because we would like to make the optic branch and the radar branch to have a similar prediction because they are characterizing the same burn area, right? So it's reasonable, and also we can adjust the consistent loss, the weight of the consistent loss, and to have a proper integrating our consideration of the unlabeled data in the target domain to improve the performance. So here, this is the learning curve. We compare like supervised loss and also consistent loss. And we can see that with this consistent loss, And UDA, the unsupervised domain interpretation, can achieve a lower consistent loss. It means that optical branch and the radar branch have a similar, with a closer prediction in detecting brain areas. And after the unsupervised domain interpretation, we also were considering that because for the target domain for the global, we have some low recent labels available, especially from FSSI, MODIS. So how could we also exploit these low recent labels to improve or further improve the generation performance? So here we proposed another here loss term, because a lower resolution labels, they are in smaller size. So here we use maxi polling, not max polling, it's average polling here to reduce the prediction size to match the shape of the prediction and low resolution labels. So we propose this weakly supervised loss so we now have three different loss terms. We have supervised loss and also weakly supervised loss plus the consistent loss. Together, we can exploit highly, maybe like the highly resolution labels, supervised loss, and unlabeled data have this consistent loss. But when we have the low resolution labels, we can also add the weakly supervised loss. Here we show the result, and we can see for Sentinel 2, we have weakly domain interpretation. Generally it have the better performance than unsupervised domain interpretation, and also significantly better than the high resolution or fully supervised model. This is Canada, this source domain, and we can see here it's we use different color to denote different approach. Like this is weakly domain interpretation. This is HR supervision. It means fully supervised with high resolution labels. And this is the UDA. And especially for the US target domain, and we can see the WDA achieves the highest accuracy compared to UDA and also the fully supervised one. And UDA also compared to this fully supervised one, UDA also performs better in the target domain. Here shows a total evaluation on the testing sites. It combines these three areas together because the testing sets includes the 2090 wildfire from Canada and the whole AK area, the Alaska area, and the US continental area. And we can see the performance is significantly better compared to these two. There's fully supervised and also it's unsupervised domain interpretation. And Sentinel 2, we also have a similar observation, and we can see this is the Canada, Alaska target domain, and also this is the total area, and we can see the weakly supervised domain interpretation achieved significantly better results than the fully supervised and also unsupervised domain interpretation. And another work we would like to briefly introduce is like we try to use SAR to optical image translation for wildfire application, because for some cases that we may have pre-fire imaging, maybe we only have one optical imaging, but we don't have maybe like because of the cloud or smoke, we cannot acquire good quality optical imagings. So we could combine the optical and the radar data together to detect the burn area and assess the burn severity. So here we use the GAN model. It also called the pixel-to-pixel model, and we would like to use here we have Sentinel 1 SAR and Sentinel 2 MSI. This is the dataset we built, as mentioned in the previous slide. So we would like to convert this SAR image into optical, and then we will to use the discriminator to decide it's to tell whether it's a real or fake imaging. And by using this architecture, we can produce fake imaging here, and then we can compare with real peripheral imaging to calculate the traditional indices like the DMBR and relative DMBR or R relative Boyne ratio. So then we can do also based on these indices to detect the burn area and also to assess the burn severity. So here we have these visual results, and like we have pre-fire center 1. Here, the first column, and also different setting, we can produce this generated post-fire imaging, and we can see that the center 1 was converted into optical corresponding optical data. And here we have the comparison, a quantitative comparison between different settings. If we based on 2 optical, pre-optical and post-optical, we achieved the highest accuracy among these 4 settings. And also, if we use real pre-fire imaging and fake or generated post-fire imaging, and we can achieve this accuracy. And based on at least 1 fake imaging, we can see that this one achieves a high accuracy. Like it's a fake pre-fire imaging and real post imaging. It means that because real post-fire imaging can provide quite accurate burn area information. It's not it's not generated from the star data. But if we use pre-star imaging and post-star imaging to generate pre and post optical imaging, and we can get this accuracy. It's quite also reasonable and significantly better than star-based. Like star-based is quite low compared to the generated result-based. And also, we are developing the wildfire monitor application. We have been working on integrating different sources of data like low resolution, high resolution, MODIS, VS, and Center 1, Center 2, Landsat together to monitor wildfires. And this is a MODIS data, and it's up to date. And this is the countdown area, and we can see some wildfire. This is active fire points. And also based on the active fire points, we can estimate the progression map and where it started and on which date it goes where, and we can see the progression history or profiles. And also here, we also have up-to-date Center 1 and 2 data available. It was developed based on the Google Scene platform, and we can have the latest data on the ongoing wildfire events. And in future, will integrate also Center 1, Center 2 based results to use deep learning model to provide up-to-date information and also more precise, more dense products than available like the MODIS daily progression map by integrating different resolutions data, also different sources data. And also, I would like to estimate, we will maybe like to produce a report that includes the burn area size and how much carbon has been released by a single wildfire event, and also to alert the risk and to prevent, to reduce loss in advance in the future. So here is some of the conclusive remarks, and we can see from this result that optical is still maybe like currently a good choice that for wildfire mapping and monitoring, and because stars still have some difficulties maybe like to detect maybe low burn severity areas, but it's useful in helping optical data to maybe have complementary information and to have more denser and more precise detection, especially when optical data was disabled. And the proposed key map, it was quite well in highlighting burning area for most of sites, but sometimes it may fail to highlight the burning areas. And TV regularization can significantly reduce the noise and increase the connectivities. Also, multi-frequency star can further increase the observation frequency, and it has a potential to bring complementary information for calculate structural changes because they are sensitive to different parts of the trees. And additionally, if you have multi-source data, maybe like the generative models can be used to combine different sources of data to produce significant better results. And additionally, to improve the cross-region generation performance, domain interpretation, our semi-supervised approach can be promising. And I think it's in the future, especially we have ongoing satellites collecting data, and we don't have tools or approach that can label this huge amount of data on a daily basis, on hourly basis. So yeah, definitely, I think the semi-supervisor will be a promising direction to go. Yeah, I think that's all. Thank you. I'm glad to take questions.
Thank you very much, Puzhao, for this great talk. So yeah, as Puzhao said, if there are any questions from anybody listening, go ahead and Puzhao might answer your questions.
Hi, Chao. My name is Luis. Thank you very much for a nice presentation.
Thank you.
I was wondering, you have all these machine learning models to detect wildfires, but the other question would be like a machine learning model to detect areas that are prone or likely to lead to wildfires, like for example, production forests where certain forest management practices have led to some conditions that might lead to extra sensitivity for wildfires. Is it something that you have considered, or do you know if anybody's working with that?
Yeah, currently we haven't worked on that. I think that there's also some groups that it's kind of more like the risk assessment. Is it right?
Yes.
Yeah, kind of like that. So you combine the information like the weather information and also moisture and also the fuel load. You combine different information together to predict the risk of this area. Will a wildfire event will happen or not, and also especially it also will be affected by the local climate especially. And yeah, that's a good point that to consider also. I see some work that they propose some approach that based on the fire modeling to estimate the risk of a specific area to have potential wildfire ignition. Yeah, but my research mainly focused on the wildfire or burn area detection based on different sources of data using machine learning algorithm by, yeah, exactly.
No, but I thought because you're working with synthetic aperture radar, and then you're talking about the characteristic and the different types of trees when they're burned and stuff, and then I thought like that would be interesting to see. For example, like thin trees that are more prone to catching fire instead of like big trees that are more resistant to fire and this kind of things.
Yeah, that's it's more like it's ecological or aspect that like the different trees, like you have different resistance performance to the wildfire or biomass burning. Like maybe some trees maybe like other wildfires, it can quickly recover to pre-fire condition, but some vegetation will disappear forever. So it will never come back again. So it's quite complex question and problems. And also I was also looking at the the post-fire recovery profiles that maybe to see how long it takes to recover to a specific conditions, like to compare to the pre-fire condition. Yeah, we'd like to dive into this point, but we just started. We haven't produced any promising results so far.
Yeah, no, thank you very much for your answer, John.
Interesting. And are there any more questions?
So I could also ask some question maybe. So it was interesting that you had studied, I mean, using different bands and so on as input to the models, that you showed some results. Another related question that I had was, have you studied to what extent the model uses the different modalities? Like maybe in some cases it might only base its decisions on certain types of bands or similar. Did you have time yet to study such effects, or?
Yeah, exactly. That's a very good point. That I see some work that in the computer vision areas, and especially when it involves different modalities data like audio and also meaning data, that it may depends more on a specific modality. Yeah, I think the like optical, it's easier to detect one areas. It may has more dependency on that branch. So here we also, yeah, definitely we will do something like to analyze the maybe like the dependency, like the optical prediction and also radar prediction, and there's accuracy compared to the ground truth, and also see there to compare. Maybe we have three prediction, and we will compare the dependency of the fusion branch on each individual prediction and their coherence and agreement. And yeah, we think if it's too depends on optical itself too much, maybe we should give more weights to the sub branch to kind of to have maybe more contribution from the star side, because you know, also, yeah, there's also other choice, like we iteratively train these two branches because in that way, maybe like we have a kind of equal dependency on these two branches individually. So we train each branch individually, and I think it would maybe, yeah, it's interesting to look into and do some experiments further. Yeah, a very good point. Yeah. Thank you, Alexis.
Another very different type of question is because you were mentioning towards the end of your talk that this research is being used also like in applications to some extent. So I was wondering, since you're also, I mean, working at KTH in Sweden, and I was wondering if you had been in touch with, let's say, Swedish firefighting services or similar regarding the research.
Yes, and yeah, I think the Professor Yifeng, and also we have some connection, and also talk to the MSP, and also previously we also have students who developed the web application that's for wildfire prediction, just based on the fire weather information and also fuel loads to predict where to go at maybe like a specific time. But yeah, it's a available model, and they developed it into a web application, but the accuracy is still not that high, still need to further improve. But I believe maybe physics-informed machine learning may have a role here. Yeah, we need to combine maybe the physics information, like because there's interaction between the atmosphere, vegetation, and also the climate, local climate. So, but it can be a very complex problem, but we hope to work with like the MSP to have maybe more knowledge from the physics model side. So hopefully to produce more promising results for fire prediction.
Thank you. Very, very interesting. Is there anyone else still with some questions maybe before we conclude?
I think I have a question. I wonder how sensitive is this to the weather? So if you have clouds or rain and stuff, I suppose the different bands will be affected differently. Have you looked into that?
Like for optical, if it's thick cloud or smoke, optical definitely is not helpful at all. We have to depend on the radar data, especially for cloud persistent areas. Like in tropical areas, we don't have the cloud-free images. We have to use radar data.
And the radar is not sensitive at all to clouds.
Yeah, usually it's not sensitive to, it can penetrate, especially if you use a long wavelength.
Okay.
Yeah. It's not sensitive to cloud smoke, also precipitation, but we see some phenomena that affected by some factors. We still not sure so far, but still we can see something from the image. It has a lower backscattering, but yeah, it could be heavy rains. Heavy rains may have some affection or effect on the SAR radar backscattering. Yeah, but for wildfire, that if the heavy rain happens, the wildfire will be put off, maybe put out. Yeah, so.
Yeah, makes sense.
Thank you for the question.
Thank you.
So yeah, I think, Leif, you might have a question.
Yeah, I have a question. Maybe you mentioned it, I'm not sure, but how robust is getting this data in a timely manner? I mean, I guess there are many sources of this data. So if you want to build this monitoring system, I mean, how often can you get data you need for these predictions? Is it collected from several central databases, and how often are these updated? And is it possible, what's the kind of resolution on these updates? Is it minutes, hours? What is it?
Yeah, like MODIS and VS, they have twice daily observation, and
from all over the world then?
Yeah, from all the world. Yeah, globally.
Okay.
Yeah, it's globally, and you have 2 images per day for MODIS and VS. But for Center-1, before the Center-1B was disabled, we have 1 imaging per 6 days, and Center-2 we have 1 imaging per 5 days. And we also have Landsat, because Landsat we currently we have Landsat 8, Landsat 7, and future we have Landsat X next. So with all these different sources of data, we definitely will have more dense observation and more maybe like we can have definitely maybe we can have maybe like a few observations during a single day, and especially if we combine with commercial data from SI, Cosmos, and also the Kabbalah space. They have like the SI, the radar data. They also have for some areas they have daily coverage, and also it's good, but it's not free to use. You you have to pay for the data sometimes. But we have all kinds of, currently we're mainly based on the free data, and we validate the feasibility and also the operationality, because also SI, they are operating at the C-band. So we can use Center-1 to maybe kind of validate the feasibility of the radar data for wildfire point area detection and monitoring. And also for Canada area, we also have the RadarSat constellation, and it's also up-to-date satellite C-band.
Okay,
yes.
so possibly it could be used as a almost real-time monitoring then.
Exactly.
Like with hourly updates or something, maybe in the best case then.
Yeah, I think it's possible. And also, there's a commercial company. It's Aurora Tech. It's a German-based company. They launched maybe some thermal satellites, small satellites. They just use a thermal satellite to monitor wildfire progression. It's funded or supported by the ESA. Yes, it's also Canada is planning to launch a wildfire set to monitor wildfires in the future.
Okay, interesting.
Yeah.
Thank you.
Thank you very much.
So yeah, I think with that, we might conclude today's session. Thank you again very much, Puzhao, for coming. And this was actually the last presentation for this semester. So we look forward to having you all back in August, and we will soon add coming speakers to the webpage. With that said, have a great summer, everyone, and see you around. Bye bye.
Alexis,
Thank you very
bye.
much.
Bye bye.
Thank you, everyone.